Most people think containers are lightweight virtual machines, but they are not. In fact, containers are just processes. Yes, the same kind of processes you see when you run a PSAUX command. But what makes containers powerful is not a virtualization. It's an isolation provided by Linux kernel, and that's the part that most people never really see. So in this video, we are going to break it down. By the end of this video, you will understand why containers feels like a separate machine, even though they are running on the same Linux host. And once this mental model clicks, tools like Docker and Kubernetes started making more sense. So let's start by looking at how we used to deploy an application before containers. So before container existed, the primary way to isolate application was using virtual machine. Each application ran inside its own virtual machines. Inside the virtual machine, we have an application. Below that, we have a guest operating system. This means every virtual machine runs its own operating system. Under that, a hypervisor provides a virtual hardware, things like CPU, memory, and the disk. And below everything, we have a virtual machine, that is CPU, memory, and the storage. Now think about this for a second. Every virtual machine includes a full operating system. So if you run 10 virtual machines, you are also running a 10 operating system. That's a lot of overhead. But container takes a very different approach. Instead of running a full operating system for every application, each container packages the application together with its dependencies like libraries, runtime, configuration, everything it needs to run the application. But notice something important here. All the containers share the same Linux kernel. Unlike virtual machine, there is no guest OS per container. There is no hypervisor managing separate operating machine. Instead, the Linux kernel itself provides the isolation. So each container gets its own isolated view of the system using namespaces. So if you see in this particular diagram, we have different namespaces for each of the container, like PID namespace that provides process isolation, network namespace that provides network isolation, mount namespace that provides file system isolation, and UTS namespace that provides hostname isolation. So a container is simply a Linux process with an isolated view of the system. So to really understand containers, we need to understand how this isolation actually works. So how do containers achieve isolation? The answer is Linux namespaces. So in this particular diagram, we have a two container running on the same host. Even though they are running on the same machine, they should not see each other. That's exactly what namespaces ensure. So each container gets its own set of namespaces. Like we have a PID namespaces for both the container that isolate processes. So a container only see its own processes. Then we have a network namespace on both the containers that isolates networking. So each container gets its own interfaces, IP addresses, and routing. Then we have a mount namespace that isolates the file system and the UTS namespace that isolates the host name. So from inside the container, it sees own processes, its own network, its own file system, and its own host name, even though everything is running on the same machine. And this is why container feel like a separate system. But in reality, they are just isolated processes, but isolation alone is not enough. Namespaces control what a container can see, but we also need to control how it can use. And this is where Cgroups comes in. So control groups allow Linux kernel to limit resources like CPU usage, memory usage, and the number of processes. So while namespaces provide isolation, Cgroup provides the control. And together they form the foundation of containers. And both are built directly on the top of Linux kernel only. But container also need their own file system environment. So when an application runs inside a container, it should see its own file, not the host one. And this is done by giving each container its own root file system. And the root file system starts at the slash. From the container's perspective, that is the entire system. So when it accesses /etc, /usr, and /var, it accesses its own isolated system. Under the hood, this is similar to how Linux uses chroot, changing the root directory a process sees. And this is why Docker images contain complete file system snapshot. They include everything needed to run the application like libraries, binaries, runtimes, and the configuration. So when a container starts, that image becomes its root file system. Now let's look at the networking as well, because container also need networking. And this is handled using network namespaces. So each container gets its own network stack. That means its own interfaces, its own routing, and its own IP address. From inside the container, it feels like it has its own network, and in practice, containers are connected using the virtual Ethernet pairs or Linux bridges. These allow containers to talk to each other and to the outside world. And the similar demo we did in our previous video, where we have established a network connectivity between the host and the network using the virtual Ethernet. If you haven't watched that video, I would recommend to check it out to get a better understanding about the network namespace. So far we have looked at the building blocks. Now the question is, how does Docker actually create a container? So when you run a docker run nginx command, it might feel like something complex is happening. But here's the reality. Docker is not doing any magic. It's simply orchestrating what Linux already provides. So Docker engine prepares everything. Then it asks the Linux kernel to create a namespaces, configure cgroups, mount the file system, and set up the networking. And finally, the kernel starts a process. In this case, that is a nginx server. And that process becomes a PID1 inside the container. And if you run the ps aux on the host, you actually see a container processes. So container is just a process. So when you run a container, you are really just starting a Linux process with isolation and resource limits applied by the kernel. In this video, we focus on process isolation and resource control. But containers also need their own file system. In the next video, we are going to dive deeper in the RootFS or the root file system environment, where we will extract the container image and explore the file system on which our container runs on. And you can see what actually inside the container image is. If you found this helpful, hit like, share it with your friends, and subscribe for more content like this. Thanks for watching. I will see you in the next one.